the email from the so I have it just so when I get email.
Okay. Everybody's turned in their take-home assignment, correct?
Someone just emailed to you again?
Yes. All right, there's a question about, Justin, what were you saying? You want what?
Just the rules and how the graph is going to go.
Rules and how the graph is going to go.
Yeah, like I guess the LCT, because I really missed it. So just
Like up, down, left, right?
let me see if
Why is Yes?
Which classes do you teach?
I teach pretty much everything that we offer here. Were you looking for a specific class or?
Well, my degree doesn't actually require an additional math class.
Okay. Well, to take another math class, you would have to take 1414. And then you could take pre-cal. Because this class is actually at the end, so it's weird. I can't get this screen to come up. If you wanted to do more math, you would have to do college algebra for STEM majors. It's not the same class. Oh no. Oh no. It's not the same class. It's a lot harder than this.
It's like the difference between bio for non-majors and majors.
Yeah, I guess so, yeah. I don't know. Okay, I can't get the computer screen to come up for some reason, and I wanted to show you some graphs today. So, I don't know what I'm going to do. I have to just do them by hand. All right, so just to reiterate the rule here, we made a table. And this table, we look at the degree of the polynomial. This is what you're talking about? Okay, and then over here we look at the leading coefficient of the polynomial. We look if it's even or odd. We look at if the leading coefficient is positive or negative. It'll go up, up, down, 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 up, or up, down, depending on the polynomial. So if you're trying to sketch, if you were asked to sketch this polynomial, you would first look at the degree here, which would be 4. N is 4. That's an even number. So you know that you're going to be looking, it's either going to be, since you're even, it's going to be one of these two, right? And then you look at the leading coefficient, which is -2, negative, right? Negative means that you are looking at this row, and so where they overlap each other, that's what you're going to be, okay? So it'll go down on the left, down on the right. Is that what you needed clarification on? Okay. All right. We are going to move on now to another type of function. So we've covered linear functions, quadratic functions, brief introduction to polynomial functions, and now we're going to talk about rational functions. And rational functions are not like, when you think of the word rational, you think about people who are rational and irrational people, right? Yeah. That's not the way this rational is being used here. When we say rational functions, it's coming from this root word ratio. And when we think ratio, we should be thinking fractions. And so a rational function is a function that involves a fraction. So how? Well, it's any function that is a fraction where the top of it, the numerator, is some polynomial. I'm just going to put poly. And the bottom is another polynomial. And a polynomial function is what we studied last class. So imagine taking one of the functions that we had last class and then dividing it by some other one. what would that create? A rational function. What do the graphs of these look like? They are messy, all right? They're really, really messy. So I think one of the best ways to get started, I'm going to silence my phone. It is silenced. Is by just going with an example, all right? So let's just start with an example of a rational function. F of x equals 2x over x minus 1. Now, you first have to ask yourself, is this a rational function? Well, we need a polynomial divided by a polynomial. Is 2x a polynomial? Yes, it is, right? What's the degree of this polynomial? 1, right? Now, it's also, if you look at it by itself, that's a line, isn't it? So I think this, I may have kind of glossed over this real quick last class. I didn't really stress it too much. We had lines, right? Linear functions, and we had quadratics. And we could write like, f of x equals mx plus b. We could write f of x equals ax squared plus bx plus c to show like what those look like. Both of these are actually in a bigger group of functions called polynomials. Polynomials, x cubed plus x squared minus 4, that's a polynomial, but so are these. So these are grouped within them. It's kind of like, if you live in Texas, you live in the United States. So every Texan is a US citizen. Every line is a polynomial. Every quadratic is a polynomial. Understand? So these two, the numerator and denominator separately, are both polynomials. So it does satisfy this, right? Okay. Now the question is, what does it look like? What's going on? Are there any interesting characteristics when we try and graph it? Can anybody tell me right away, like, where we might have a problem with this function? Think of plugging numbers into this function. Are you going to ever have a problem plugging in any numbers? What? Yeah, what if the denominator is 0? See, because with fractions we can't divide by 0, right? So what if I asked you right now to plug in 1, right? This means plug 1 into the function. You would go 2 times 1 on top over 1 minus 1 on the bottom. You would get what? 2 over 0. And what's 2 divided by 0? It's undefined. That's never happened, right? With lines and with parabolas and with the polynomials from last class, we could plug any number in because we never had fractions, right? We never had our variable down in the bottom like this. So this is a new aspect that we have not investigated yet. Understand? So there's a major difference already between these and polynomials. Let's see. Let me ask you now, what about the X-intercepts for this? If I asked you to find an X-intercept, you would do the standard technique. What's the standard technique for finding X-intercepts? Set the function equal to 0, right? So I'm going to take this and set it equal to 0. Now pay very close attention to what I'm about to do. What did I do? Do what?
Multiplied by x negative 1.
X minus 1, yes. What I did here, it's not the same thing. What I did here is I took the left side of this equation and I multiplied by x minus 1. And I did the same thing on this side. And what happens is it goes away on the left side, right? These cancel with each other. And then over here, 0 times anything is 0, right? So if you're ever trying to find, and this is what I wanted you to pay close attention to, if you're ever trying to find the x-intercepts of a rational function, then you're going to just need to look at when the numerator is 0. That's all you have to look at. Investigate when the numerator is 0. And when would that happen? Divide both sides by 2, and you just get 0. 0 over 2 is 0. 2 over 0 is not 0. Okay. See that? So we do have an x-intercept. Agreed? So I'm going to try and start drawing this for us, just to get an idea of what it might look like. So I think I'll do my graph right over here. So I have my x and y axes over here. And I know that at 0, right, I have an x-intercept. And then I have something very interesting happening where? Where did I say we had a problem? When x was 1, right? So I'm just going to come over here and I'm going to mark 1 right here. And I know that I can't plug 1 in, so I'm not going to have a dot anywhere, above or below, right? There's no dot ever. It's undefined. So I'm going to draw a dotted line like this. This is not part of the graph. It's just to help me with the graph, so I remember that I can't ever put a dot on that dotted line. All right, so let me try and find some other characteristics, some other behaviors that this thing might have. How about we try and find some other points on the graph just to get a feel for what's happening? All right, so I'm going to just start plugging in some numbers, doing what we used to do way back in the day. I don't know if you ever remember doing this, something called a t-table, where you do something like this. Here's x, here's f of x. Remember doing this ever? Okay, let's just try and get a feel for what's happening. So I would like to plug in some numbers. How about if we plug in -1? What would happen? Let's plug -1 in here. We would have what on top? What's 2 times -1? -2. What's -1 minus 1? -2. And this is just 1, right? Understand? 1. So at -1, I go up 1, and I can put a dot there. With me? Let's keep going. Let's go out further this way. Let's go with we'll do -2. So what's 2 times -2? -4 over what's -2 minus 1? -3. What's -4 over -3? Positive, it's positive, right? 1.333 forever, okay? 1.333 forever. So at -2, I'm up at, what, 1.33? Let's just say it's about right here. If this is 2, we're up a little bit more, right? Let's go even further out. Okay, let's go to -10. See what's happening. What's 2 times -10? -20 over what's -10 minus 1? -11. Now, someone on their calculator, please do that for me. What's 20 divided by 11? 1.9. What is it? 1.81? Now, my graph, way out here, -10, I'm at. Why do you think I keep on going out to the side over here? What do you think I'm trying to determine?
It's linear.
It can't be linear. I mean, this is not a straight line. The only thing that's going to look like a straight line are linear functions. That's it. So remember with polynomials, I gave you that table. You know, we just did it to start off the class. Even, odd, plus, minus, and that gave us our left and right behavior right away. Right? With rational functions, it's a little more complicated. It's not as simple. But I'm trying to figure out what's happening as I'm going out this way. I'm trying to find the left-hand behavior right now. What is that?
It's growing.
It's growing, right? Doesn't it look like it's growing? Now the question is, does it keep going forever? So let me get real extreme here. Let's go out to negative 1,000. So that's out of the room, across the lake probably. Maybe not that far. Okay, way out there. Plug it in. What's 2 times negative 1,000 is negative 2,000 over what's negative 1,000 minus 1? Negative 1,001. Do that on your calculator. 1.9, what? 1.99? So it grew a little more, didn't it? But it seems like it's growing and never passing up something, right? It's never getting bigger than 2. And you could check it for yourself. Go out to negative 10,000. Go out to negative 100,000. Go out to negative a billion, a trillion. Doesn't matter. You're never going to go past 2. I promise. It's never going to happen. So when we graph it, this is what we've got. Okay, like this. And then imagine, I'm going to do it in a different color. Imagine an imaginary line that's at 2. Imagine this imaginary line up here that's acting like a horizontal barrier, all right? And what it's doing is saying, what? This line right here is saying to the function, come to me, right? Come to me, but don't touch me, all right? You're just going to keep getting closer and closer to this, but never, ever touch it. All the way out, as far as you go. So you'll keep on getting closer and closer and closer and closer, but you'll never actually get there. Right? That's what the left side of this looks like. All right? Okay. Well, that's what happens out the left side. What about what happens out the right side? What happens if I replace all of these numbers with positive numbers? Let's see what would happen. Okay, how would it change this one? This would become, what? Oh, I can't do 1. Right? Can't do 1. We can take this one out. How about 2? What happens if I replace this with 2? What is the top going to be? 4 over 1. Y'all okay with that? I'm assuming you could plug these in and figure them out, which is 4. I'm going to take this one out of here. Okay. What about if I replace 10? It would be positive 20. And then what about the bottom? 9? Can someone do that for me? 20 divided by 9? 2.22. And then the last one would be 2,000 over what? 999? 2.2? 2.002, something like that. Wow, that looks like it started out here at 2, and it was up at 4, which was up here, right? And then when I went out to 10, it went down and down. And guess what? It's getting closer and closer to what? To 2, but it's never going to get to 2. But instead of being below it like this one, right, is always smaller than 2, on this side, it's above it. So it looks like this. I'm going to go off camera, so I'm going to exaggerate this. It's doing that sort of thing. And we have this horizontal line that's like, come to me, right? That's the left behavior, that's the right behavior. Yes?
Okay. How do we know without doing the calculations that it will not go above or below 2?
Like when it comes time for you to do this, are you going to have to do all this? Is that what you're saying? Or are you asking me if there's an easier way to do this? Yes. Going to get to that, but I want to at least like build up to what these look like, why they look like this, and then we'll have some shortcuts. All right? There's still some piece of the graph that I have not addressed. And that's, we know we can't plug in 1, but what about something in here? What would happen if I take a number in here, like let's say 1/2? Pardon? Well, let's plug it in. Let's actually plug 1/2 into the function, and let's see what we get. So if I plug in 1/2, what do I get up top? What's 2 times 1/2? 1. What's 1/2 take away 1? Negative 1/2. Now notice the fractional line here. 1 divided by negative 1/2, you flip it up and it becomes what? Negative 2, right? Because this is negative. So this is going to become negative 2. Do you see that? Y'all okay? It's one of those days where I wish I could do a cartwheel. I've always wanted to be able to do a cartwheel. Because I thought, you know, on days like this where my whole class is like this, I could just do a couple of cartwheels and people would be like, holy shit. And like wake up. Yes? I can't do the cartwheels. Just imagine cartwheels right now. Can you plug that in and get negative 2 comfortably? So here, I go down 1, 2. So I'm here, right? Let's get even closer to 1. So what would be really close to 1? How about 0.9? Now we'll have to use our calculator for this. Let's try 0.9. So if you do 0.9 into this, 2 times 0.9 is 1.8 over what's 0.9 minus 1? 1.8, you get negative 0.1, don't you? And if you get it on your calculator, that's going to be what? Negative 18. So where are we? Way down there, right? If I try something even closer, like that, and I'll let you do it on your calculator. If you did that, you know what? I have mine. I'll just tell you what it is. Do you agree 0.9999999 is even closer to 1? But it's not 1. So if I do 2 times 0.9999, on the top I get 1.9998. And then if I do 0.9999 minus 1, I get 0.0001. And if I, negative, sorry. And if I divide the two, 1, 2, 3, 4, 2, 3, 4, I believe I get negative 19,998. Negative 19,998. Which means if I get even closer to 1, where am I? Way down there, right? Way down. And so can you see that what's happening here is that it's diving down like this? As you move closer to 1, it dives down to, we would say, to negative infinity is where it's headed. Follow? Little side note question here. What is the number right to the left of 1? 0.99? That's it? What about 0.999? What's that? 0.99999 forever? What do y'all think? Is there a number right next to 1? Is there a closest number? Like, do you understand what I'm asking you? Kathleen? 0.999 forever, right? 0.999 with a bar on top, I think, is what is being proposed as the number that's right next to 1. How many of you would agree with that or see that kind of makes sense? Maybe. Okay. All right. You want an answer? Okay. No. There is no number right next to 1. It's impossible to find a number right next to 1. Right? Because if you go right to the left of 1 and say, that's the number, I guarantee you that you've missed an infinite number of numbers. It's guaranteed. Now, what I'm going to show you here is even crazier. All right, watch this. Everyone see this? I'm going to show you that that is not the number right next to 1. See if I can convince you or not. All right. Let x be equal to 0.999 forever. All right, everyone? I come in here, I'm going to tell you right now, x is 0.999 forever. You happy? Okay. What is 10x? So what happens when you multiply a decimal by 10? What happens? Decimal point moves over 1, right? Right? Do you agree? So do you agree that this would be 9.999 forever? Do you agree with that? Okay, so we're all happy? All right, so now let me ask you this. What's 10x take away x, everyone? Forget the 0.999. If I just algebraically come in here and say, hey, hello, everyone, what's 10x minus 1x? How many x's would you have? 9 x's. Agreed? But what was 10x? 9.99 forever. What happens if I take away x from that? What's x? 0.999 forever. What would happen if I subtract these two? What would you be left with? Just 9, right? This tail part, the 0.999s forever, would cancel with these 0.99s forever. And you'd just be left with 9. What that means is that if you let x be this, and then 10x would be this, then 10x minus x should be this, but that's the same as this, which means these are equal. And if 9x equals 9, then what's x? 1. So what I'm here to tell you is that 0.99 forever is 1. So there is no number right next to 1. 0.999 forever is the number 1. Yeah, it's kind of weird, all right, but that's the way it is. So the reason I'm saying this is because as this thing starts to dive down and start to go this way forever, right? Some people will say, well, you eventually get to that last number before 1. And the thing is, you never are going to get there. There's always numbers in between. There's a classic example, of what happens if I'm trying to walk across the room, and what happens if I go half the distance, stop, and then go half the distance, stop, and then go half the distance again, stop, and keep doing this, stop, half, stop, half, stop, half, stop. Am I ever going to get to the wall? I'll never get to the wall, because you can always half something. You'll always be able to half something. Okay. All right. So this is the behavior of this function. On the left side of 1, it starts diving down, right? So you almost look at this like as you're moving from left to right, the function's just happy, and then it sees this red barrier and it goes, shit, I've got to go somewhere. I can't hit that wall. I'm going to go down and keep going down. All right? Now, on the other side, the function over here is going like this. What happens is you move from right to left as you start to get close to 1. So if we were to take a number in here like 1.5 and plug it in, guess what? It would be further up. If we plug in something really close to 1 on this side, 1.1, we would be even further up. And you'll just have to trust without us making a table that this thing's going to do the same thing on this side. It's never going to hit that red line. Got it? Okay. This is the graph of this rational function. This is it right here. Very awkward looking graph, right? It doesn't look anything like a line, doesn't look anything like a parabola, doesn't look anything like a polynomial, which were like roller coasters. Lines, parabolas, and polynomials, you can all draw them without picking up your pencil. Rational functions, most of the time, at some point to draw it, you have to pick up your pencil. Like if I'm trying to just draw the whole thing, I have to go like this, pick up my pencil, and then do this part. All right, so we have very important names for these interesting places on the graph. This right here, of course, is our X-intercept. This vertical thing right here, this vertical line, is called a vertical asymptote. Asymptote. Vertical asymptote. I will abbreviate this VA from now on. Now, here's the thing about vertical asymptotes. You are never allowed to draw your graph across them. So you cannot cross a vertical asymptote, ever, ever, ever. All right? This one right here, it's horizontal, right? This is called a horizontal asymptote. And this, I'll abbreviate HA. Now the rules on horizontal asymptotes are a little different. Horizontal asymptotes, the way I want you to see these as being like, I like to use the analogy of like a magnet. You know how a magnet likes to draw things towards it? I mean, of course, you can push things away too, but most of the time we think magnet, you think it's going to pull something towards it, right? These horizontal asymptotes are like magnets, and they pull our function towards them. But this is only end behavior only. You have horizontal asymptote, it's on each end, right? And it tells you what the end of your function, what the ends of your function do, and that's all it tells you. It tells you nothing about the middle. Remember how we had question marks last time with that table? Right? Question in the middle, we had to go figure it out. Horizontal asymptote will tell you what happens at the ends. The middle, you have to go figure out. All right, well, y'all look thrilled, let me tell you.
It's not always going to be 1 and 2.
1 or 2. Oh, no. Every single rational function is unique in the way it looks. You may have multiple vertical asymptotes. You can have none, you can have 1, you can have 5, you can have 10. It just depends. I'm going to keep it in this class to maximum of maybe 2 or 3. All right? Just going to draw something up here. Lines, parabolas, polynomials, and then this is just some basic characteristics. That's what a line looks like, right? Parabolas can open up or down. Polynomials look like this. We said lines were good for, like, you know, modeling someone losing weight, or you're getting paid so much for a job, right? Lines were pretty good at that. Constant rates of change. Parabolas good for, you know, things being dropped on Earth, things like that. Polynomials, I showed you the problem with the box, right? Trying to put something together and maximize, you know, or maximize the volume, right? So when are these important? Like, why would we ever use something like that, a rational function in the real world? Well, there's many, many applications of rational functions, but I like to refer to a movie. You may have, let's see if anyone can tell me what movie this quote is from. And I may not get it word for word, so on a long enough timeline, the survival rate for everything drops to 0. Anybody recognize that? The Notebook? No, that's not the Notebook. No? No. What? No. No. Fight Club. Who's seen Fight Club? Okay. All right, so it's towards the beginning. Okay, how many of you have seen Fight Club? If you have not seen it, then you're not going to know what I'm talking about. You know how he's an insurance, not sales guy, but he's an insurance adjuster, and he's talking about how his company, they go and they figure out like what's the probability of a person wrecking their car, and you multiply it times the probability of this, and then you figure out like all this stuff. In that scene, somewhere around there, he talks about this. On a long enough timeline, the survival rate for everything drops to 0. So think about this. Here's time. And let's just think about humans, and let's just think about, just take your average human, right? They start off, let's say, at time 0, being a healthy baby, right? What's the probability that they're alive? Well, it's pretty high, right? Because they're alive. We're assuming that when we start saying, okay, you're alive. All right, they're alive. So it's pretty high. And then on a long enough timeline, the survival rate, the probability that they're still alive, drops to 0. So goes like that. And then you imagine this horizontal asymptote. So maybe the probability that they live to be, 50 years old, this is in years, let's say. Probability that you live to 50 years old, pretty good, but not as good as living to your first birthday, right? And then you get out to, I don't know, this isn't a good scale. Maybe I'll make this 20. Then we get out here to 100. What's the probability that someone's going to live to 100? It's smaller than living to 20, right? Agreed? And then you can start talking about males versus females and all that stuff. But now, what happens when I get out here to 200? What's the probability that somebody is going to live to be 200 years old? I saw that. What does that mean?
Pretty
small or 0? So it's very small. But are you saying is it 0? There's a huge difference here. Okay, that's a good argument, right? Nobody's ever lived to be 200 that we know of, right? Right? It's dropping to 0, but is it 0? I mean, if you're going to say that it's 0 here at 200, that it's actually 0, okay? Like there's no chance you're going to live to 200, right? Then what about 180? Still 0? Like at what point is it not 0? It's dropping. It's getting closer to 0. So let me try and rephrase it. What are the odds that you're going to win the lottery? Let's just say they do what, weekly drawings? What's the probability that you're going to win this week's lottery? Good? Small? Small, right? Small chance that you're going to win the lottery. But you could win, right, if you play? What's the probability that you win the lottery 2 weeks in a row? What? Okay. What's the probability that you win the lottery 2 weeks in a row? Even smaller. Possible? Okay, what's the probability that you win the lottery every week, 52 weeks in a row? For the entire year, you win the lottery every week. What's the probability? Infinitesimally small, right? Could it happen? Has it ever happened? Okay, that's what we're talking about here. 200, it's not possible. You can't say that. Nobody's ever done it, but who knows, right? It's infinitesimally small. Maybe you have better odds of winning the lottery 52 weeks in a row than you do to live to be 200. Maybe those odds are better, but it's possible. So we need a function that models this sort of thing. You can't use a line because the line is going to get to 0 at some point. You can't use this because it goes down and then turns back up, so you can't use that. You can't use this because it's, you know, undulating up and down. We need something that models that sort of behavior where you're trying to get closer to something without actually getting there. Rational functions are perfect for that sort of scenario. And so they're useful for us, right? All right, I'm just trying to show you some value for studying these, all right? Yes?
Okay, so out of curiosity, if you took into account like accidents, like broken body parts or something, into the graph, then technically it would be a polynomial, right?
Well, there's a lot of things, right? Because, you know, getting through the first year of life is usually, you know, harder. That's why I said in a general picture, you know, this might undulate a little bit in the beginning, and then, you know, you might have some things, but eventually it's going to drop off. So what you might have to do is modify the rational function so that it does that. You can make a rational function that will behave this way. But then it gets more complicated, and then, you know, that's why you have to take more and more and more math classes to get models that are better and better and better for the real world. All right, well, I hope that you have some appreciation maybe for rational functions. Let's see, what am I going to ask you to do for homework? What am I going to ask you to do on the test, right? Now everyone can sit up and pay attention. Here's an example. I'd like for us to sketch this rational function. So is that a rational function? Yes? Okay. Now, you know how I've given you steps for all of these functions? I've given you like a process. I'm going to do a process for this also, and I'm going to do it separately over here. Steps for sketching rational functions. What's the first step? Is it a rational function? Rational function? Yes or no? So is this a rational function? Is it a polynomial divided by a polynomial? Yes. So first step, check. So this is the way I'm going to do this. I'm going to do what the step is. I'm going to come over here and do the step. Go over there. What's the step? Do the step. Second step. And I would like to put a little asterisk, okay, up here, because I am presenting this to you in a way that I understand you were in 13-14, not in 14-14. And I'm more speaking to the camera because it's somebody who might find this video later knows that there's a lot more involved to sketching a rational function than what I'm going to give you, because I'm only going to give you certain types of rational functions that behave a certain way. Okay, so I'm leaving out steps. Right? That just makes me good with the math gods in case it ever comes up later that, like, I'm okay, I didn't show the wrong thing, all right? This will be good enough to get you through rational functions. Okay, so we check that it's rational. Next thing, hey, let's find the x-intercepts, right? Let's just start by trying to find some points on the graph. So we'll get x-intercepts. And how did I tell you to find the x-intercept? Set the function equal to 0, right? But I told you that if you have a fraction, all you have to worry about is the numerator, right? All you have to do is the numerator. So next to this, I'm going to put set numerator equal to 0 and solve. I'm afraid I'm going off camera here. Let me just see. Nope, I'm good. Set the numerator equal to 0 and solve. So let's do that over here. So what am I going to do? Set what to 0? X plus 3 equal to 0. And we get x is negative 3. And I'm just going to remind you this is a point on the x-axis. Step 3. Find the vertical asymptotes. Now, I didn't show you how to do that, did I? No? So you have this in your notes. I'd like for you to go back and look at that problem we just did. Where did that vertical asymptote occur? Go ahead.
On the denominator?
Yeah, it was whenever this was 0, right? Which was when x was 1. So to find the vertical asymptote, what you do is you set the denominator equal to 0 and solve. Pardon?
B4?
Be what? Oh, for this problem. I'm sorry. I thought you were telling me I'm on step 4. I'm sorry. Okay. So for this, you set denominator equal to 0 and solve. So let me do that over here. Step 3, the vertical asymptotes. I set the denominator, which is x minus 4, equal to 0, and solve, and I get x is equal to 4. Now, in my picture, what is this? Because this right here was a point on the x-axis, right? Is that a point on my x-axis? No. What is this? It's that vertical barrier, right? That concrete wall that our function cannot go through, right? So this is going to be a vertical dotted line. That's what that's going to be. What's the other characteristic of the rational function that we had that was important? The horizontal asymptote. So how do we find those? This is the hardest one to do, right? This is the hardest one. Find the horizontal asymptotes. I wish I could tell you it's something like set this equal to 0 or something like that, but it's not. There are 3 different scenarios that we can have. Okay, case A. We're going to have 3 cases. Case A, B, and C. Case A is when the degree of numerator, I'm just going to put num, is that all right? Numerator and denominator are the same. Bless you. Do we have that case here? Yes. So cartwheel, 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 and we continue. All right, so do we have that case here? Yes. The degree of the numerator is 1 and denominator is also 1, right? So we have that case. What happens in this case? Well, the horizontal asymptote is a horizontal line. It's y equals the LC of the numerator divided by the LC of the denominator. What does LC mean? Leading coefficient. Now, remember, we have two other cases. We have case B and case C, right? So please, on your notes, or in your notes, leave some space for case B and C. I'm going to do two more examples after we finish this one. That'll show you case B and case C. All right? So case A, we check the powers, right? If these powers are the same, if those powers are the same, then what we do is we look at the leading coefficients. So what's the leading coefficient of this one? 1. What's the leading coefficient of this one? 1. And if you take 1 and you divide it by 1, you get 1. Y equals 1. So remember, y is up and down. If we move up 1, we're going to have dotted lines at the edges. 1 unit up. Look back at the previous problem we did. It was this. Right? This right here. Is this case A? Yes. We have the same degree, right? 1 and 1. So what are the leading coefficients? 2 and 1. What's 2 over 1? 2. And remember there were 2 at the edges? That's why. Understand? No questions on that? Okay. Yes.
2 at the edges, that means that's why y was 2.
Yep, that's why it was going up toward, yeah, it was going up towards that magnetic 2 thing, pulling it. That's why it comes from this. All right. We've got everything. There's one more thing that we'll need in order to finish the graph, and that's step 5. And this part just sucks, okay? It's tedious. Test points. I forgot to put step 4 over here, sorry. So 4, for this problem, we were in case A, right? Case A, check. And so we did y equals 1 over 1, 1 over 1, which was 1, and that's it. I mean, y equals 1. And this is going to be a horizontal magnet. I'm going to say magnet. I know it's cheesy, but it's a horizontal magnet, and it's ends only. Step 5, let's put test points, but before that, put plot info and then test points. What I mean by plot info is I want you to actually plot all the information you've gathered on a graph first. Then we're going to do something called test points. So you ready? We're ready to put this all together. By the way, rational functions are the hardest functions to graph, by far. The steps are the most involved, okay? So if this seems like, man, that's a lot to do to graph a function, yes, that's the way they are. We're going to study another function after this called exponential functions, and those are really pretty easy to graph. All right, so I'm going to draw my picture now. And I'm going to need your help. Give yourself plenty of room to draw this. Let's start with the first step. Well, we checked it was a rational function. Second step, what did we find? X-intercept, right? Where was it? Negative 3. So I'm going to come over here, and what am I going to draw here at negative 3? A dot, right there on the x-axis. All right, what was the next thing I found? Where was it? Positive 4? 1, 2, 3, 4. Here at 4, and what am I going to draw here? Dotted vertical line. I'm going to do it in a different color because I want to remind you it's not part of our graph, right? It's just to help us. We just remember we can't cross that. Got to pick up my pencil when I get there. Next piece of information. Horizontal asymptote, where was that? 1, y equals 1, right? So on the y-axis, go up 1, mark it. And then I want you to draw a horizontal dotted line at the ends only. I'll do it in green. Only at the ends. So what do I mean by the ends? I mean, like, this is the last piece of information we have, right? Like, what's over there is like a big mystery, right? That's where I want you to put the dotted line. It's very dangerous to put it across the middle. The reason why it's dangerous is because if you see it in the middle of your graph, you'll think you can't cross it. You can cross it in the middle. It only tells you what happens at the edges. Now, as much as I say that, students are going to draw this all the way across. And if you go get help in the tutoring lab, a lot of the tutors draw it all the way across. It's not a good practice. And then over here, I'm going to do the same thing. The last piece of information I have over here is this vertical, right? To the right of that, it's like a big abyss. I don't know what's over here. So I'm going to put this over here, like this. Got it? That's your picture so far. Unfortunately, this right here is not enough information for us to be able to draw the picture. We need some more information. And that's where this last part comes in, and that's test points. You're going to make a table, basically, and you're going to plug in some points. But the points you plug in are, it's very specific on what you need to do. You just don't want to pick random points. It's very specific. You're going to look at your X-intercepts and your vertical asymptotes. Okay? Y'all pay attention to this because test points is one of the harder parts of the problem, and people just forget about it and they don't know what they're supposed to do. You're going to pick a test point on each side and in between every vertical asymptote and every X-intercept you see. So think about it. Here's -3. I need something on both sides of it. All right? So I have to pick something over here. Anything you want. What do you think? -4. I'm going to put a little X there, not a dot, because I don't want to accidentally think that's part of my graph. And I'm just going to mark -4. And I'll make it. I'll add this to my t table. I'm going to actually plug in. I'm going to plug in -4 into my t table. Here's x, f of x. Now, I need something on the other side of it. -2, -1, 0, 1, 2, 3. Any of those numbers would work. You want -2? Okay. Put a little x there, -2. All right. So for this x-intercept, I have something on each side, right? Okay. Now, do I have any other x-intercepts? No. Now look at your vertical asymptotes. I need something on each side of this. So how about to the left of it? I already have something to the left of it, don't I? Isn't this already to the left of it? I can use that one. I can reuse that one. Okay, so I don't have to do another one. You can if you want, but you don't have to. Do I have something to the right of it? No. So anything you want out here. 7. There you go. 7. So I'm going to have to pick, I'm going to use 3 test points right there. And unfortunately, you have to plug these into the function. Okay? Yes?
Is there an event where you have more than one x-axis or x-intercept?
X-intercept?
Yeah.
Stay tuned.
Okay.
It's coming. There's a rule of thumb that you can use for this. If you add up how many x-intercepts you have and how many vertical asymptotes you have, and add 1, that's how many test points you should have. So how many x-intercepts do I have? X-intercepts. 1. How many vertical asymptotes do I have? 1. Add those together. 2. Add 1 to that. 3. You should have 3 test points. That's all you'll need. So if I had 2 x-intercepts and 2 vertical asymptotes, then I would need 5 test points to do it correctly. All right, I already erased the function. What was it? X, oh, I can tell you.
Over
X plus 3. So if I do -4 plus 3 over -4 minus 4, that's it, right? It was x plus 3 over x minus 4.